In a time long ago, when the world was still a realm of mystery and wonder, a journey of discovery began that would change the course of science forever. This is the story of the development of atomic theory, a journey through the minds of brilliant thinkers who dared to explore the unseen world of particles. Let's explore the captivating journey of atomic models, uncovering the driving forces behind scientific curiosity and the challenges they face in unraveling the mysteries of the atom. Our story begins with the ancient Greek philosopher Democritus, who lived around 460-370 BCE. Democritus pondered the nature of matter and proposed the idea of atomos, meaning indivisible. He suggested that everything is made up of tiny, indivisible particles called atoms, each with its own unique properties. Though his ideas were met with skepticism, they planted a seed of curiosity that would sprout in later centuries. In the early 19th century, there lived a diligent and inquisitive scientist named John Dalton. He was known for his keen interest in the properties of matter and his unyielding pursuit of unraveling the secrets of the universe. Dalton was fascinated by the idea that all matter was made up of tiny, indivisible particles called atoms. He envisioned these atoms as the fundamental building blocks of everything in the world. With careful observations and meticulous experiments, Dalton proposed his revolutionary atomic theory. A model that was proposed by John Dalton in 1804. He believed that the world of matter was made up of tiny round particles like little spheres that formed everything around us. It was an intriguing idea, but as time passed and knowledge grew, matter wasn't just made of the spheres, but it was composed of even tinier, more intricate building blocks. J.J. Thomson is best known for his discovery of the electron and his work on the nature of cathode rays, which paved the way for the understanding of atomic structure and the development of the atomic theory. A model that was supported from Dalton was made J.J. Thomson embark on a thrilling quest to uncover the secrets of the atom. Armed with available data, he imagined that atom as a sphere with embedded charges, like the Dalton's billiard balls. But Thomson's imagination soared higher as he introduced tiny negatively charged particles called electrons within the atom's positively charged body. To put his vision to the test, he conducted the awe-inspiring cathode ray experiment, revealing the existence of these elusive electrons. Thomson's ingenious model and groundbreaking experiment forever transformed our understanding of the atomic realm, leading the way for future scientific exploration. His model faced some challenges. He couldn't provide any real-world proof for his idea, and when other brilliant minds like Rutherford conducted experiments, Thomson's model couldn't explain the results. Ernest Rutherford's groundbreaking experiment with alpha particles in 1909 shattered Thomson's model. Rutherford's result led to the conclusion that atoms had a small dense nucleus at their core, surrounded by electrons in orbit. This planetary model paved the way for a deeper understanding of atomic structure. When particles are fired at a thin gold sheet, most pass through but a few are deflected. This suggests that atoms consist mostly of empty space with a tiny dense nucleus. Rutherford's experiment revealed that nearly all the alpha particles he aimed at gold passed straight through. This led him to infer that the atom contains a concentrated positively charged nucleus, while the remainder consists mainly of empty space. Niels Bohr, a Danish scientist, agreed with Rutherford's model of the atom, but also knew that it had a few problems. Using his background in quantum physics, he was able to improve Rutherford's model. He was able to explain why the electrons did not merge into the nucleus. Niels Bohr likened electrons to dancers circling an atomic nucleus just like planets orbit the sun. These electrons could switch dance floors or orbits based on their energy levels. Picture electrons as party guests. The shiny ones choose lower energy orbits first. When those are full, the bold electrons occupy higher energy orbits. Erwin Schrödinger electron cloud model states that electrons dwell in fuzzy eons like the clouds, rather than well-defined orbits. He improved on Bohr's findings. Erwin Schrödinger was a physicist who came up with the atomic model that we still use until today. Because of his model, the idea that electrons move in a fixed orbit was debunked. In the fascinating atomic realm, Schrödinger revealed that electrons don't stick to fixed orbits. Instead, they occupy a cloud-like zone around the nucleus, where they are likely to be. There is a great probability of seeing the electrons where the cloud is most dense, and where the electron is less likely to be, the cloud is less dense. The dense areas in these clouds are electron orbitals, the favorite spots for these elusive dancers. From the initial seed of curiosity planted by Democritus to the intricate web of particles described by the Standard Model, the development of atomic theory has been an epic journey. It's a tale of brilliant minds, daring experiments, and paradigm-shifting discoveries that have shaped our understanding of the fundamental nature of reality. As we gaze into the subatomic depths, we continue to push the boundaries of knowledge, driven by the same human spirit of exploration that has fueled scientific progress throughout the ages.